Uncertainty and the Wave. The Parallel Paths of Werner Heisenberg and Erwin Schrödinger. Episode 1. A New Dawn in Physics. Werner Heisenberg was born on December 5, 1901, in Würzburg, Germany, into a world where the foundations of classical physics seemed solid. His father was a professor of Byzantine history, and his upbringing instilled a deep appreciation of scholarship. Erwin Schrödinger, slightly older, was born on August 12, 1887, in Vienna, Austria. The confluence of their upbringings and personal interests set them on paths that would intersect in the radical transformations of physics during the early 20th century. As children, both were precocious students, fascinated not only by mathematics and the natural world, but also by broader cultural and philosophical questions. While Heisenberg demonstrated an early talent for mental calculation and problem-solving, Schrödinger displayed an inclination for contemplative thought, a love of poetry and philosophical speculation that would remain with him throughout his life. In the latter half of the 19th century, the edifice of classical physics was built upon the bedrock principles of Newtonian mechanics and Maxwell's electromagnetism. These theories had been experimentally and mathematically refined to an impressive degree of precision. If you asked a physicist in 1890 whether the world of physics might soon see another conceptual earthquake, the most common answer might have been that we were nearing completion of our understanding of nature. Indeed, the successes of classical physics in describing planetary motion, electromagnetism, and thermodynamics seem to leave little room for dramatic upheaval. Yet, by the dawn of the 20th century, a series of puzzles began to shake this confidence. Max Planck's work on blackbody radiation in 1900 introduced the radical notion that energy could be quantized. Planck found that to resolve the ultraviolet catastrophe, he needed to posit that the energy of oscillators in the walls of a blackbody was not continuous but discrete, proportionate to integer multiples of hn, where h is Planck's constant and n is the frequency. This was a desperate trick, in Planck's own words, but it worked. Not long afterward, Albert Einstein used this quantum hypothesis to explain the photoelectric effect, arguing that light itself could behave like discrete packets of energy, photons. The world was changing, though not always in ways that were immediately recognized or understood. For every young physicist who saw the new quantum ideas as a bold leap forward, there were senior figures who remained skeptical. Yet the ensuing decades were a whirlwind of new discoveries and theoretical propositions. Niels Bohr introduced his model of the hydrogen atom in 1913, combining classical orbits with quantum jumps for electrons. That model explained spectral lines in a way previously impossible, but it also raised new questions, leaving open the deeper mysteries of atomic structure and electron behavior. By the time Heisenberg and Schrödinger began their serious studies, the theoretical scaffolding of physics stood in a strange, incomplete condition, classical-like shells on the outside, but with disjointed quantum patches that were starting to appear. Heisenberg's early years were suffused with a strong classical education, but his passion for mathematics soon drew him into the orbit of Arnold Sommerfeld at the University of Munich. Sommerfeld's school was a leading center for theoretical physics, known for training bright minds like Wolfgang Pauli. Heisenberg was quickly recognized for his aptitude, and in the early 1920s, he joined the circle of physicists around Niels Bohr in Copenhagen. Bohr himself was forging new ideas about the atom, but it was also in Copenhagen that Heisenberg found an environment that tolerated bold speculation. His restless mind, acute mathematical skill, and aversion to interpretative fluff pushed him to construct something entirely new. Meanwhile, Erwin Schrödinger's intellectual life took shape in Vienna's rich cultural milieu. Born to a well-off family, he grew up in a home where scientific inquiry mingled with literature and art. His early schooling at the Akademisches Gymnasium in Vienna emphasized the humanities, languages, and philosophy as much as mathematics and science. He read Schopenhauer and other philosophers with deep interest, even as his scientific curiosity remained piqued. Schrödinger studied physics at the University of Vienna, receiving strong influences from Franz Exner and Friedrich Hasnerl. The latter was famously known for exploring the relationship between mass and energy shortly before Einstein formalized it. During the tumultuous years of World War I, Schrödinger served in the Austrian army as an artillery officer, yet still managed to keep up with scientific journals and thoughts on the newest developments in physics. When the war ended, Europe was drastically changed. Economies were shattered, empires collapsed, and an entire generation grappled with the aftershock. In spite of the ruin, the scientific community pressed on, and the 1920s became a golden era for quantum thinking. An international network of brilliant physicists, Bohr, Pauli, Born, Dirac, de Broglie, and many others, propelled the field forward with unprecedented speed. For Heisenberg, the path to quantum mechanics was one of methodical, often nerve-wracking leaps of abstraction. For Schrödinger, it was a natural outgrowth of his philosophical preoccupations and a stroke of inspiration sparked by Louis de Broglie's doctoral thesis, which posited the wave nature of matter. The lingering question that overshadowed all these developments was, how does nature really operate on the smallest scales? Though the Bohr model predicted spectral lines well, it lacked a coherent mathematical framework for more complex atoms or phenomena. Old quantum theory consisted largely of a grab bag of rules and quantum conditions insufficient to paint a complete picture. It seemed that a more fundamental rethinking of the relationships between position, momentum, and energy, and the role of measurement itself, was needed. When Heisenberg arrived at his great breakthrough, he was not working in isolation. He had, in effect, come to a fork in the road. Either keep patching the old quantum theory or attempt a radical rewriting of the fundamentals. The necessity of explaining experimental data, particularly spectral intensities for more complicated atoms, pushed him. Under Bohr's guidance in Copenhagen, Heisenberg aimed to banish what he deemed unobservable elements from theory, discarding classical orbits around an atom's nucleus. Instead, he wanted to build a formalism directly around measurable quantities, such as transition frequencies and intensities. This approach would become known as matrix mechanics. For Schrödinger, the impetus was a deep conviction that something more continuous, more mathematically elegant, might underlie the quantum realm. He found de Broglie's notion of matter waves enthralling. If electrons had wave properties, perhaps the electron in an atom could be described by some wave function. Schrödinger guessed that the solution to the riddle lay in a wave equation that could describe the behavior of matter in terms akin to classical wave phenomena. He was living in Zurich at the time, a place of relative stability in a Europe still feeling the after-effects of war, and his readiness to unify quantum phenomena under a wave perspective shaped his entire approach. Thus, as the mid-1920s approached, the stage was set for one of the greatest intellectual showdowns in the history of physics. Both Heisenberg and Schrödinger were inching toward what would become two distinct, yet ultimately equivalent, formulations of quantum mechanics. Each man's personal style reflected their respective formalisms. Heisenberg's matrix mechanics were abstract, discrete, and arguably more difficult to intuit at first glance. Schrödinger's wave mechanics were continuous, differential, and reminiscent of classical field equations, offering a more familiar aesthetic to many theorists. Yet the significance of their work would not remain limited to dusty tomes of physics journals. Their discoveries, along with their debates, would unleash philosophical torrents, reshape the boundaries of scientific inquiry, and highlight fundamental questions about the nature of knowledge, measurement, and reality itself. As they strode forward in constructing these radical new frameworks, they were buoyed by a circle of equally brilliant contemporaries, Born, Jordan, Dirac, Pauli, Bohr, and others, who collectively pushed quantum theory to a conceptual revolution unmatched since the days of Newton. To understand why these two men, Heisenberg and Schrödinger, forged different paths, one must appreciate the currents in early 20th century thought. On the one hand, the tradition of analytical mechanics with Lagrangians, Hamiltonians, and continuous fields remained strong. On the other hand, the discrete energy levels and Einstein's photons suggested that classical continuity might no longer be the final word. Heisenberg, guided by his vision of banishing unobservable orbits, wanted a purely quantum mathematics that didn't rely on classical pictures at all. Schrödinger believed that something akin to the wave concept, continuous in space and time, ought to be the bedrock of nature's description. Each approach solved the same physical problems, most famously the hydrogen atom's energy levels. But the difference in interpretation, as well as style, sparked heated controversy. One of the cornerstones of classical physics had been the ability to know, in principle, all the relevant dynamical variables, position, momentum, energy, and so on, at the same time. Under quantum mechanics, this classical dream would be shattered. The idea that one could measure with arbitrary precision every property of a particle was beginning to look untenable. Heisenberg, through his exploration of matrix mechanics and the commutation relations, discovered that certain pairs of variables, such as position and momentum, did not commute, meaning their product depends on the order in which they are multiplied. This non-commutativity soon led to his famous uncertainty principle, specifying that the product of the uncertainties in position and momentum has a lower bound. It was an intellectual bombshell. Schrödinger was equally revolutionary. His wave equation captured the evolution of the wave function, the fundamental descriptor of a quantum system. The solutions to Schrödinger's equation accurately described energy levels of the hydrogen atom and, more generally, a host of phenomena that had perplexed physicists. The wave function, however, had peculiar implications for how one interprets the nature of a particle. Does the wave function represent a real physical wave in space? Or is it merely a probability amplitude for finding the particle at a given location? These were among the vexing questions that soon consumed the luminaries of the field, yet the differences did not stop there. The personalities of Heisenberg and Schrödinger, shaped by their backgrounds and philosophical temperaments, led them to interpret quantum theory in distinct ways. Heisenberg's impetus was to excise classical pictures and rely on the mathematics of operators tied to experiments. Schrödinger, inclined toward a more classical worldview, was motivated by the idea of continuous fields, reminiscent of the lines of force in electromagnetism. This difference would form the crux of their scientific and philosophical divergences. Matrix versus wave mechanics, operator versus wave function, discrete versus continuous. Even in the earliest days of their breakthroughs, both men recognized that quantum theory would not be an isolated phenomenon in the intellectual cosmos. It implied a fundamental limit to what could be known about the micro-world. It also suggested that the act of measurement cannot be viewed as a passive window into nature, but as an active intrusion that changes the system. By mid-decade, heated discussions broke out at conferences such as the famous Solvay gatherings, where the likes of Einstein, Bohr, and others tested each other's arguments in a realm beyond mere mathematics, asking what these equations said about reality itself. Nor should one separate these developments from the broader cultural and historical context. Germany, and Europe at large, were still reeling from the devastation of World War I. Economic turmoil, political upheaval, and intellectual ferment made the 1920s an era of both anxiety and creative explosion. It is not surprising that radical new ideas in physics found resonance in a generation that had seen the collapse of old political structures. The quantum revolution mirrored broader shifts in culture and thought, as certainty and Victorian order gave way to fragmentation, existential crises, and new forms of expression, whether in art, literature, or science. Amid this swirl, Heisenberg's and Schrödinger's breakthroughs did not fully settle the nature of quantum reality. Instead, they opened the door to bigger questions about the role of the observer, the meaning of probability, and the possible existence of hidden variables. As the two frameworks of quantum mechanics were shown to be mathematically equivalent, thanks in part to the work of Paul Dirac and John von Neumann, physicists were forced to grapple with the idea that different mathematical pictures could represent the same underlying physical theory. The question shifted from which is correct to how do we interpret the mathematics physically and philosophically. Their personal journeys from bright students to architects of quantum theory were shaped by mentors, the war, and a remarkable network of collaborators and correspondents. Heisenberg, through his travels to Göttingen, Copenhagen, and elsewhere, was always at the heart of quantum controversies, working closely with Max Born, Pascual Jordan, and later with Wolfgang Pauli. Schrödinger took a more peripatetic route, moving from Vienna to Zurich, from Jena to Breslau, and other temporary academic posts before finally landing in Berlin, briefly, and then in Oxford, following the Nazi rise to power. During the mid-1920s, though, both men were deeply immersed in forging the quantum revolution. Their achievements formed the bedrock for all that followed in 20th century physics, from the understanding of chemical bonds and the periodic table to semiconductors and lasers to the creation of nuclear technology. Yet these massive practical outcomes were not on the minds of Schrödinger and Heisenberg as they battled with integrals, commutators, and boundary conditions in search of a new conceptual grammar. They were driven by the intellectual challenge, the puzzle of nature, and the sense that old physics was insufficient to describe the newly revealed quantum domain. They were also shaped by their generational vantage point. Heisenberg, having been too young to fight in World War I, was able to devote himself more fully to research as soon as he was old enough for advanced study. Schrödinger, on the other hand, was not only older, but had experienced the war directly. That experience left a mark on his outlook. The sense that the world could undergo cataclysmic ruptures fueled his desire for a theory that was elegant, unifying, and deeply grounded in mathematical structure. Both men, in different ways, expressed a hunger for coherence, for a worldview that would bring sense to the illusions and half-truths that seemed to dominate the older theories. By the middle of the decade, the stage was set for quantum mechanics' final shape to emerge. Heisenberg, upon forging matrix mechanics in 1925, had laid a crucial piece of the puzzle. Schrödinger's wave mechanics appeared in 1926, causing immediate excitement and even relief among physicists who found the wave approach more intuitive. At that point, the story could have ended with triumphant acceptance of wave mechanics. But then came the demonstration that Heisenberg's operator form and Schrödinger's wave equation were equivalent in predictive power. This unexpected unity took the field by storm, uniting the discrete worldview of quantum transitions with the continuous worldview of wave phenomena. However, the puzzle was far from complete. There remained, and to this day there remain, profound interpretative challenges. The new quantum mechanics, despite its spectacular predictive success, said disconcerting things about reality. Heisenberg's soon-to-be articulated uncertainty principle exemplified this. The notion that one cannot know simultaneously the exact position and momentum of a particle. Classical determinism, in the sense of Laplace's demon, was finished, and Schrödinger, who might have hoped to salvage a more deterministic wave ontology, eventually introduced his own famous thought experiment. The cat in the box that is, in a sense, both dead and alive until observed. The philosophical consequences were staggering, forcing a re-examination of the nature of consciousness, measurement, and the classical quantum boundary. In these early days, though, the heavy philosophical questions simmered in the background while the scientists hammered out the mathematics and tested it against experiments. Heisenberg, never shy about challenging classical assumptions, felt confident that the new quantum theory must drastically revise our fundamental concepts. Schrödinger, by contrast, initially believed wave mechanics might restore a form of realism, albeit in wave form. Over time, he grew more perplexed about what the wave function really meant as the measurement problem loomed larger. Thus, the quantum revolution roiled forward. When the dust settled by the late 1920s, Heisenberg and Schrödinger stood as two pillars of the new theory, flanked by Bohr, Born, Dirac, Pauli, and others. What had begun as a niche concern over atomic spectra turned into a generational shift in physics. Nothing in science would remain quite the same. Even Einstein, whose early work helped birth quantum ideas, was unsettled by the turn toward probability and uncertainty. It was not that quantum mechanics was incomplete, he argued. Rather, he suspected there might be a deeper, perhaps hidden variable theory under its probabilistic veneer. But the stage was set. The new theory advanced, and Heisenberg and Schrödinger took their places among the greatest thinkers of the modern age. In episode 2, we will see how these men refined and defended their respective viewpoints, how the so-called Copenhagen interpretation took shape, and how Schrödinger's wave equation and Heisenberg's matrix formalism became recognized as two faces of the same coin. We will delve deeper into the core conceptual leaps and see them in direct conversation, sometimes cordial, sometimes contentious. The continuing transformation of physics would also echo in the broader culture, changing how people conceived of knowledge itself. But it all began here, with these two brilliant minds forging parallel, seemingly competing roads to one overarching goal: understanding the quantum realm in a coherent, mathematically rigorous, and conceptually innovative way. Episode 2. Forging the Quantum Frameworks. By 1925, Werner Heisenberg was 23 years old, fresh from his doctorate under Arnold Sommerfeld and a stint working with Max Born at the University of Göttingen. He brought a fresh perspective unencumbered by old habits. That summer, while suffering from hay fever, he traveled to the island of Helgoland in the North Sea to find respite from pollen and focus on the intractable problems of atomic physics. Isolated on that windswept island, he performed a series of mental gymnastics that would result in his first paper on what would become matrix mechanics. It was a breakthrough forged from a simple philosophical principle. Theories should be constructed only from observable quantities. In classical physics, position and momentum were not just observable, but were considered definitional parameters of a system's state. If quantum systems defied precise orbit descriptions, Heisenberg reasoned, then the concept of orbits might be superfluous or even misleading. Instead, he focused on the frequencies and intensities of the light emitted by electrons jumping between quantized energy states. From these transitions, he built tables or arrays that encoded how a system transforms from one energy state to another. Through collaboration with Born and Pascual Jordan, these arrays were recognized as matrices, mathematical objects that could multiply but not necessarily commute with each other. This non-commuting property signified a radical departure from classical mechanics. This commutation relation would form the backbone of Heisenberg's theory and lead directly to the uncertainty principle. In matrix form, these operators express transitions, not definite classical quantities. The method worked brilliantly for calculating spectral lines, something the older quantum theory struggled to do systematically. Heisenberg, Born, and Jordan refined the formalism into what they called matrix mechanics. It was, in many ways, a revolution in how physicists understood physical reality. Around the same time, Erwin Schrödinger, then a professor at the University of Zurich, was on a parallel quest. Inspired by Louis de Broglie's 1924 thesis, which posited that particles like electrons might be associated with a wave of wavelength lambda equals h/p, Schrödinger hypothesized that the electron in an atom could be described as a standing wave. He set out to formulate a wave equation that governed these matter waves. By December 1925, he had found the beginnings of what we now know as the Schrödinger equation. Early in 1926, he published a series of papers laying out the formalism, starting with a treatment of the hydrogen atom. The results matched the energy levels previously discovered by Bohr and matched the matrix mechanics predictions, but derived from a continuous wave perspective. Schrödinger's equation accurately reproduced the energy spectrum of the hydrogen atom, but it also suggested that the electron wasn't just a point particle orbiting a nucleus. Instead, it was described by a wave function that spread out in space. The interpretation of this wave function was initially debated. Did it represent a physical wave, or was it something more abstract? The reaction to Schrödinger's wave mechanics was immediate and enthusiastic among many physicists. Compared to matrix mechanics, which demanded familiarity with non-commutative algebra and somewhat abstract mathematics, wave mechanics seemed more intuitive. It aligned with the prevailing success of field theories like Maxwell's electromagnetic theory, offering a continuous picture reminiscent of classical waves. Within months, Schrödinger followed up with additional papers that extended his method to helium and other systems, building confidence that wave mechanics was the comprehensive new approach to quantum phenomena. Then came the surprising demonstration that wave mechanics and matrix mechanics were mathematically equivalent. Schrödinger himself tackled the problem by applying a suitable mathematical transform, the Fourier transform, among other tools. One could switch between the wave function representation and the matrix operator representation. This showed that the quantum revolution had birthed not two contradictory theories, but two formulations of the same underlying framework. Although equivalence was proven, the philosophical rift remained. Heisenberg and Schrödinger drew different lessons about what the quantum formalism meant. Their personalities, as well as their philosophical influences, shaped these interpretations. Heisenberg, a product of the Göttingen and Copenhagen schools, embraced the idea that we should avoid speaking about properties of a system that cannot be measured experimentally. The quantum world, for him, was irreducibly described by probabilities. He was comfortable with an operational stance. The quantum formalism enumerates the outcomes of possible measurements, and that is physics. The abstract algebraic formalism of matrix mechanics was consistent with this operational approach. Schrödinger, in contrast, harbored the hope that the wave function was a real physical wave. He was intrigued by the possibility that wave mechanics might restore a sense of continuity that had vanished with the discrete jumps of the old quantum theory. Over time, he became increasingly uncomfortable with the standard Copenhagen interpretation, which designated the wave function as a probability amplitude that collapses upon measurement. Schrödinger felt that something in that notion was incomplete, leading him eventually to propose his famous cat thought experiment in the 1930s, an attempt to show how bizarre such collapses would appear on a macroscopic scale. The scientific community as a whole absorbed both frameworks in short order. By the late 1920s, a new generation of physicists began to unify these approaches under what might loosely be called the standard quantum theory. Mathematically, Paul Dirac played a key role in bridging them into a more general formalism, culminating in his transformation theory. John von Neumann later provided a rigorous mathematical foundation in his 1932 treatise, Mathematical Foundations of Quantum Mechanics, establishing Hilbert spaces as the setting for wave functions or state vectors and linear operators for observables. Yet, in the mid-1920s, these developments were not simply academic triumphs. They provoked existential debates exemplified by Einstein's repeated challenges at the Solvay conferences. Einstein, though he recognized the success of quantum mechanics, insisted there must be a deeper deterministic theory, famously remarking, "God does not play dice." Heisenberg and Bohr, among others, retorted that the notion of determinism was out of place in the quantum realm, that nature itself was governed by probabilistic laws. Schrödinger, caught somewhat in the middle, found himself leaning more toward Einstein's discomfort. He saw wave mechanics as possibly bridging the gap, though he too recognized the success of the probability interpretation in practice. For Heisenberg, the crowning achievement of his 1920s work came with his 1927 articulation of the uncertainty principle. He arrived at this principle by examining the commutator structure of quantum operators and the idea that measurements interfere with one another. A measurement of a particle's position inevitably disturbs its momentum and vice versa. More abstractly, the wave function that is tightly localized in space has a broad spread in momentum space, reflecting a fundamental limitation on simultaneous precision. This discovery was not merely a technical detail, it became a pillar of the new worldview, raising the idea that certain classical questions about a system's state simply have no well-defined answers in quantum theory. Schrödinger's wave mechanics also contained within it the seeds of the uncertainty relationship. In fact, Schrödinger himself derived a version of the principle shortly after Heisenberg, noting that the wave equation's Fourier transforms connected position space and momentum space wave functions. But he was never as enthusiastic about proclaiming the end of classical determinism. He was more interested in the wave function's potential to unify everything into a single continuous field. Even so, he recognized that his wave theory, as it was usually interpreted, forced a probabilistic meaning onto the square modulus of the wave function as the probability density for finding a particle at a given location. From 1926 to 1927, the conversation around quantum mechanics coalesced at conferences, letters, and lectures. Heisenberg and Schrödinger corresponded with each other, sometimes politely, sometimes more pointedly. Heisenberg found Schrödinger's reliance on an actual wave picture suspicious, while Schrödinger was wary of the dryness and discontinuity in Heisenberg's operator approach. At the Solvay Conference of 1927, for example, an iconic group photo of the greatest physicists of the era captured a moment of convergence and tension. Einstein, Bohr, Heisenberg, Schrödinger, Marie Curie, Max Planck, Paul Dirac, and others. Behind the scenes, the participants engaged in animated debates about complementarity, uncertainty, wave-particle duality, and the meaning of measurement. It was during these conferences and through extensive letter writing that the so-called Copenhagen interpretation began to take shape. Bohr, Heisenberg, and Pauli, with varying degrees of alignment, championed the idea that quantum mechanics does not describe an objective reality independent of measurement devices, but rather defines relationships between observations and the mathematics of the theory. The wave function, in this view, represents our knowledge of the system rather than a physically real wave. Measurement outcomes do not reveal pre-existing properties, they bring about the properties. Schrödinger was ambivalent about this. He admired Bohr greatly and respected Heisenberg, but found the idea of a purely epistemic wave function unsatisfying. Throughout his life, he continued to explore alternative interpretations, including attempts to formulate a wave-only perspective without collapse. His intellectual restlessness would eventually produce the Schrödinger's cat paradox in 1935, illustrating how quantum superposition, if taken at face value, leads to a cat that is simultaneously alive and dead until observed, a clear sign of interpretative tension. Meanwhile, Heisenberg continued refining the operator approach, working closely with Born, Jordan, and Pauli to expand quantum mechanics into multi-electron atoms, quantum electrodynamics, and nuclear physics. His technical mastery combined with a philosophical bent rooted in the tradition of logical positivism, or at least a certain brand of operational thinking. Yet he was never merely a narrow instrumentalist. He read Plato, engaged in philosophical discussions with Bohr and others, and believed quantum mechanics had forced a reorientation of the concept of objectivity. By 1928, the dust had settled enough that quantum theory began to be taught in universities in some nascent form. Textbooks incorporating elements of Schrödinger's wave mechanics, Heisenberg's matrices, and Dirac's transformations began to appear. For the broader scientific community, the main question was no longer whether quantum mechanics was correct. Experiments with atomic spectra, electron diffraction, and the newly discovered scattering phenomena consistently matched the predictions. The question became how to interpret it. In an environment where the new generation of physicists was open to radical ideas, Heisenberg and Schrödinger achieved celebrity status. Their differences, ironically, helped bring about a consensus. The math worked, and it worked brilliantly, so whichever representation one preferred was a matter of taste and convenience. If you felt more comfortable solving differential equations, Schrödinger's wave mechanics was your method. If algebraic manipulations and operator theory appealed to you, Heisenberg's matrix approach was there. The theory was robust enough to handle either path. Still, that did not stop the continuing philosophical conversations. Schrödinger's stance evolved over time. He recognized that wave mechanics, while more intuitive, did not banish the oddities of quantum phenomena. There remained the measurement problem and the collapse postulate, that the Copenhagen school invoked. Heisenberg, for his part, grew more convinced that the new quantum theory signaled a fundamental shift from classical realism toward a reality shaped by measurement and potentialities. They debated in papers, in letters, at conferences, and in the halls of universities around Europe. Then, inevitably, life began to intervene more forcefully. Political and economic turbulence in Germany and Austria, the looming shadows of rising nationalism, and the shockwaves of the Great Depression increasingly shaped academic careers. Heisenberg, a German national, found himself soon contending with the transformations in German academia under the Nazi regime. Schrödinger, an Austrian, witnessed the political unraveling of his homeland as well. This historical context would impact their personal and professional trajectories, though in the mid to late 1920s, before the crisis fully manifested, the scientific optimism about quantum mechanics was still unbridled. The synergy of wave and matrix mechanics opened new frontiers that neither Heisenberg nor Schrödinger could have foreseen in detail. Chemists rapidly adopted quantum mechanics to explain molecular bonding, giving rise to quantum chemistry. Astrophysicists began to interpret stellar spectra with a quantum lens, gleaning new information about the composition and life cycles of stars. Over the next decade, more advanced theories of quantum electrodynamics emerged, leading eventually to the standard model of particle physics in the second half of the 20th century. Practically every facet of modern physics, from superconductivity to semiconductors, has its roots in the synergy of Heisenberg's and Schrödinger's frameworks. Yet the story of quantum mechanics in these pivotal years is also, at its heart, a human drama. Two brilliant physicists, coming from different backgrounds, guided by distinct philosophical intuitions, arrived at deeply linked mathematical formalisms. Their interactions with peers like Bohr and Born shaped the final outcome. The debates and controversies forced them to articulate their ideas with increasing clarity, culminating in a theory so empirically robust that it remains unassailable to this day, even as theoretical physicists search for new frontiers beyond the standard model. It is often said that scientific revolutions occur when the old guard fades and the new guard presses forward. In the case of quantum mechanics, the shift was generational. Many older, established physicists struggled to come to terms with the dissolution of classical determinism and the infiltration of probability into the heart of physics. Younger physicists, meanwhile, embraced the new quantum worldview, forging ahead to solve real problems in spectroscopy, chemical bonding, nuclear transitions, and more. Heisenberg and Schrödinger, both relatively young when they made their breakthroughs, symbolized the ascendancy of a new era. That new era would soon face the crucible of world events. Heisenberg would remain in Germany during the Nazi regime, becoming embroiled in controversies regarding his role in the German nuclear effort. Schrödinger, deeply uncomfortable in the increasingly hostile environment, moved repeatedly, seeking academic havens in Oxford, Graz, and eventually the newly founded Institute for Advanced Studies in Dublin. Their personal journeys, shaped by political, cultural, and moral issues, would reflect the larger tragedy of Europe in the 1930s and 1940s. But their quantum work, by then, was already foundational, etched into the core of modern physics. In Episode 3, we will delve into the climax of their scientific rivalry and synergy, explore Heisenberg's articulation of the uncertainty principle in greater depth, trace Schrödinger's cat paradox, and see how both men and the broader community adapted to the swirling philosophical controversies. We will also see the first glimmers of how quantum mechanics would be co-opted, for better or worse, by technological and political developments leading into World War. The forging of quantum mechanics as a robust theory was almost complete, but how it was interpreted and used would soon become matters of profound historical significance. Episode 3: Philosophical Fault Lines and the Uncertainty Principle. The late 1920s were a crucible for Werner Heisenberg and Erwin Schrödinger. Their theories were accepted, but how to interpret them was far from settled. Meanwhile, they were joined by other leading lights, Niels Bohr, Paul Dirac, Wolfgang Pauli, each adding intellectual heft to the conceptual framework. The success of quantum mechanics in predicting experimental results was undeniable, yet the underlying meaning of the formalism was a fertile ground for debate. The center of that controversy was Bohr's Institute in Copenhagen, where Heisenberg had often visited, and where the seeds of what became known as the Copenhagen interpretation took root. Heisenberg, perhaps more than anyone else, carried forward the banner of a new worldview, one in which the classical picture of particles with definite trajectories was replaced by discrete transitions and the mathematics of non-commuting observables. To him, the mathematics led to an inescapable conclusion. There are fundamental limits to how precisely one can know complementary variables, position and momentum, energy and time, etc. When he formally derived this in 1927, the uncertainty principle was enshrined in the foundations of quantum theory. The principle stated that the product of the uncertainties in position and momentum has a lower bound. If one tries to reduce the uncertainty in position to near zero, the uncertainty in momentum increases accordingly, and vice versa. Heisenberg initially explained this in terms of measurement disturbance. Imagine using a photon to locate an electron. The higher the photon's frequency, to get a sharper image of the electron's position, the larger its momentum, and thus the greater the recoil imparted to the electron, spoiling precise knowledge of its momentum. Bohr refined the explanation. Even in principle, independent of any measuring device, the formal commutation relations implied a limit to knowledge. This was not just a matter of experimental technology, but a matter of principle rooted in quantum structure. The unveiling of the uncertainty principle shook the foundations of classical thought. Philosophers and physicists alike grappled with its meaning. Was determinism dead? Did events at the quantum scale proceed randomly, or was there a hidden variable theory lurking beneath the formalism? Einstein, famously a champion of realism, resisted the notion that quantum mechanics was the final word on the matter. Though he acknowledged the empirical success, he insisted that a deeper theory might restore causality. He expressed his doubts in letters and at conferences, pushing Bohr and Heisenberg to defend their position with more nuance. At the same time, Schrödinger's wave equation had fully taken hold in the community. To many, wave mechanics offered a more palatable approach than matrix mechanics. It allowed for visualization. Electron orbitals in an atom, for instance, were simply standing wave patterns of the wave function. The shapes of s, p, and d orbitals, so familiar to modern chemistry students, emerged straightforwardly from Schrödinger's equation. But the wave interpretation left a puzzle. If the electron were literally spread out as a wave, how and why did detection events appear as point-like impacts? In 1927, Schrödinger wrote a paper titled The Interpretation of Quantum Mechanics, in which he tried to salvage a more classical wave viewpoint. He advocated for what might be considered a wave-realistic interpretation, but he could not entirely evade the measurement problem or the discrete detection events that seemed at odds with continuous waves. While Schrödinger was a brilliant mathematician and thinker, he found the leap to accepting wave function collapse to be unsettling. Thus, philosophical tensions bubbled up. Heisenberg, with Bohr, Pauli, Born, and Jordan, leaned toward the notion that we should avoid talking about properties of a system that cannot be measured experimentally. The quantum world, in their view, was irreducibly probabilistic. Schrödinger, and sometimes Einstein, clung to the possibility that the wave was real, or at least pointed to some deeper, possibly deterministic explanation. The two men, Heisenberg and Schrödinger, both recognized each other's brilliance and the equivalence of their formalisms, but their philosophical instincts were divergent. The mid to late 1920s also saw the broader scientific community begin to incorporate the quantum revolution into various subfields. Chemists found that wave mechanics elegantly explained chemical bonding, particularly covalent bonds, through the overlap of wave functions. Astrophysicists used quantum principles to interpret stellar spectra more accurately. Experimentalists observed phenomena like the Compton effect, electron diffraction, and the Zeeman effect, all consistent with the new theory. In this sense, quantum mechanics was unstoppable as a scientific tool, even as the philosophical questions remained hotly debated. Heisenberg, keenly aware of the philosophical dimension, wrote extensively on the matter. His early writings expressed an operationalist viewpoint, reminiscent of the logical positivist circles in Vienna, although he was never strictly a positivist. He believed that the theory's formalism was the best we could do to describe reality at the atomic scale. The notion of a classical trajectory was, in his view, not just unknown, it was meaningless if it could not, in principle, be observed. Schrödinger, by contrast, maintained that the wave function was a real entity in a higher dimensional configuration space, and tried to interpret quantum jumps or collapses as something emergent or approximate rather than fundamental. As the 1920s turned to the 1930s, the scientific community witnessed an uneasy equilibrium. Quantum mechanics worked, the mathematics was set. Matrix and wave formulations were recognized as different paths to the same results, and one could choose whichever was more convenient for a given problem. In principle, you could transform wave functions into matrices or vice versa, but the interpretative rift persisted. Bohr's complementarity principle, introduced around this time, posited that wave and particle descriptions were complementary pictures, each offering partial insight. One could observe interference, wave property, or localization, particle property, depending on the experimental setup, but never both fully at once. Heisenberg found Bohr's complementarity in close harmony with his own thinking. Schrödinger, though intellectually respectful of Bohr, saw complementarity as a statement that sidestepped the deeper question of the wave function's ontological status. He worried that quantum mechanics, as championed by the Copenhagen school, might be incomplete, or at least might not be the final statement of nature's fundamental processes. Amid these conceptual struggles, life intruded. The Weimar Republic was collapsing into economic chaos. In 1933, Hitler came to power in Germany. Jewish physicists and those deemed political opponents were forced out of their positions. Many emigrated to the United States, the United Kingdom, or elsewhere, causing an intellectual diaspora. This changed the academic landscape drastically. Schrödinger, who had moved to Berlin in 1927, faced moral and political dilemmas under the Nazi regime. He soon left Germany, spending time in Austria, then Oxford, and eventually settling in Ireland, where he helped establish the Institute for Advanced Studies in Dublin. Heisenberg chose to remain in Germany. He did not join the Nazi Party, but neither did he openly oppose the regime. Over the years, he found himself labeled a proponent of Jewish physics by certain nationalist circles because of his allegiance to Einstein's theories and to quantum mechanics, which these extremists considered suspect. Still, Heisenberg managed to navigate the treacherous political waters, continuing his research and teaching. By the end of the 1930s, he became embroiled in research on nuclear fission and the potential for an atomic bomb, though the extent of his complicity or reluctance in the Nazi nuclear program remains a subject of historical debate. Through all this turmoil, Schrödinger and Heisenberg continued to refine their thinking about quantum mechanics. Schrödinger, now exiled from Germany, wrote several papers in the mid-1930s that pushed the boundaries of interpretation. In 1935, in response to Einstein, Podolsky, and Rosen's famous EPR paradox, which questioned whether quantum mechanics could be considered complete, Schrödinger introduced the concept of entanglement. He recognized that quantum states could become correlated so that measuring one part of a system instantly determined properties of another, no matter how distant. This was a new puzzle, challenging classical ideas of locality and realism. It also presaged the later debates culminating in John Bell's theorem in 1964 and the experimental tests by Alain Aspect in the 1970s and 1980s. Around the same time, Schrödinger crafted his famous cat thought experiment as a critique of the Copenhagen stance on wave function collapse. In the experiment, a cat is placed in a sealed box with a mechanism that has a probability of killing the cat based on a quantum event. Until the box is opened and observed, quantum theory seemingly implies the cat is in a superposition of alive and dead states. Schrödinger intended this as a reductio ad absurdum, highlighting how bizarre it would be to accept that a macroscopic being could exist in superposed states. Ironically, the Schrödinger's cat analogy became a staple illustration of quantum weirdness in popular culture, overshadowing Schrödinger's own skepticism about the standard interpretation. Heisenberg, too, wrestled with the conceptual issues, but he tended to emphasize that quantum mechanics was the final revolution needed to address the atomic realm. Philosophical distaste for probabilistic outcomes missed the point. In a series of lectures and publications throughout the 1930s and 1940s, Heisenberg argued that quantum theory forced a new epistemological stance, that reality at the atomic scale could not be divorced from how we measure it. The mathematics of the theory provided all that could be said meaningfully about atomic events. In short, by the late 1930s, Heisenberg was a leading proponent of the idea that quantum mechanics, in its Copenhagen form, was complete, and that attempts to restore classical realism were misguided. Schrödinger, meanwhile, was never fully convinced. Although he accepted the correctness of quantum mechanics in its predictive power, he felt the need for a more coherent or less measurement-centric interpretation. Their disagreements highlighted fundamental philosophical divides about what science can and should say about the nature of reality. The uncertainty principle, by this point, was a fully integrated part of physics. Experiments on electron diffraction, for example, confirmed that attempts to localize electrons more precisely in position inevitably produced larger spreads in momentum. The principle also fed into the development of nuclear physics, helping to explain why electrons do not crash into the nucleus, as classical electromagnetism might have suggested, and why protons and neutrons exhibit zero-point energy in a nucleus. These insights bridged the gap between theory and experiment and helped ensure that Heisenberg's name was etched into the annals of physics history. Schrödinger, though not the father of an equally famous principle like uncertainty, had endowed physics with the wave equation, arguably the single most important piece of the quantum framework from a practical standpoint. The Schrödinger equation became the fundamental tool for tackling bound-state problems, chemical structures, and beyond. Its conceptual clarity in many contexts endeared it to successive generations of physicists, but neither man was a monolith. Both displayed wide-ranging interests outside physics. Heisenberg, as a young man, played piano with near-professional skill and was keen on philosophical readings, especially Plato. Schrödinger was famously broad in his cultural and intellectual pursuits. He had a penchant for literature, Eastern philosophy, and importantly, biology, leading him eventually to write What is Life? In 1944, a seminal book that influenced the future founders of molecular biology, including Francis Crick. In Episode 4, we will see how the events of World War II and the subsequent geopolitical climate shaped the lives of Heisenberg and Schrödinger. We will also examine Schrödinger's foray into biology and his wide-ranging philosophical speculations. As the two men navigated a world once again in turmoil, their quantum legacies remained firm, yet their personal paths diverged significantly. Even so, their theories, matrix mechanics and wave mechanics, remained the dual pillars upon which the quantum edifice stood, continuing to inspire new generations of physicists who would grapple with the same questions of interpretation that had energized these giants. Episode 4: War, Cats, and Uncertainty. With the 1930s drawing to a close, the dark cloud of war overshadowed Europe once again. The Nazi regime extended its grip, culminating in the invasion of Poland in September 1939, which triggered World War II. Academic life across the continent was upended. Physicists found themselves conscripted into war projects, some willingly, some under duress, and some exiled. Werner Heisenberg, by now a respected professor in Leipzig, was soon drawn into discussions about a possible Uranverein, uranium club, to explore nuclear fission for Germany's war effort. Erwin Schrödinger, having left Germany years earlier, ended up in Austria briefly, But after the Anschluss in 1938, he made an escape, eventually securing a position in Ireland by 1939. He was spared the moral and political entanglements Heisenberg faced. During the war years, Heisenberg's role remains one of the most contentious chapters in the history of science. He took the helm at the Kaiser Wilhelm Institute for Physics, later the Max Planck Institute, and along with other German scientists, investigated the chain reactions needed for nuclear power or a potential bomb. Scholars continue to debate the extent of Heisenberg's involvement and intentions. Some argue he did just enough to keep research going while secretly thwarting the development of a German atomic bomb, cognizant of the moral implications. Others believe he miscalculated the feasibility and resources required, inadvertently slowing the project. Whatever the truth, Heisenberg's war years cast a shadow over his legacy, leading to acrimonious debates in the post-war period, particularly with figures like Edward Teller and others involved in the Allied nuclear programs. Schrödinger, in contrast, was sheltered from the direct horrors of war in Dublin at the newly established Institute for Advanced Studies. There he continued to pursue theoretical physics and the philosophy of science. He was also deeply engaged in writing and thinking about biology, culminating in the publication of What is Life in 1944. This short book, though not directly about quantum mechanics, attempted to explain how living organisms maintain order and replicate in terms of quantum principles and statistical physics. Schrödinger's speculation that the hereditary material might be an aperiodic crystal famously inspired the likes of James Watson, Francis Crick, and Maurice Wilkins in their quest to discover the molecular basis of heredity. This was a remarkable instance of the quantum revolution crossing disciplinary boundaries to spur new breakthroughs in biology. Back on the continent, Heisenberg continued to refine quantum field theories, partially bridging them with nuclear physics. Although war consumed the daily reality of Europe, theoretical work persisted at a subdued pace. Many of Heisenberg's students and collaborators were drafted or scattered, but he maintained a research circle. Toward the end of the war, he was briefly captured by Allied forces and held in England under Operation Epsilon, alongside other German nuclear scientists. Tapes from those detentions revealed the tangled ethics and personal justifications swirling in their discussions. The war ended in 1945 with Germany's defeat. News of the atomic bombs dropped on Hiroshima and Nagasaki shocked the world, including the physicists who had long considered atomic energy to be a theoretical curiosity. The post-war years brought a reckoning for those who had remained in Germany. Heisenberg, though not accused of war crimes, faced hostility from colleagues who questioned his moral stance. Yet he was allowed to resume scientific work, helping to re-establish the Max Planck Institutes and revitalize German science. For Schrödinger, post-war Europe offered renewed possibilities. He visited the continent periodically and for a time even returned to Austria, though he did not stay permanently. In Ireland, he continued his wide-ranging intellectual pursuits, giving seminars that blended quantum theory, biology, philosophy, and Eastern thought. He was never as directly embroiled in war politics as Heisenberg, and his personal reputation, while marked by controversies of a different nature, he led a somewhat bohemian personal life, was never as ethically fraught in the public eye. Amid these divergent wartime narratives, the fundamental contributions of Heisenberg and Schrödinger to quantum mechanics never waned in importance. Indeed, the bombs that ended the war underscored the power of quantum theory. Nuclear fission, at its core, is a quantum phenomenon. Tunneling and discrete energy states govern nuclear stability. The design and working of atomic bombs were, in part, outgrowths of the quantum revolution. Although neither Heisenberg nor Schrödinger directly built the bombs, their discoveries, along with the entire quantum community, laid the scientific groundwork that made such weapons possible. This intersection of quantum theory with horrific destructive power forced physicists to reflect on their roles in society. Einstein, who had earlier urged Roosevelt to develop an atomic program, though he later regretted it, famously declared that had he known the potential, he would have become a watchmaker instead. Others, such as Oppenheimer, confronted a moral crisis after seeing the devastation wrought by nuclear weapons. While Schrödinger did not directly work on war projects, he was acutely aware of how quantum mechanics had influenced nuclear science. Heisenberg found himself the target of both suspicion and admiration. Some saw him as a loyal German who attempted to keep scientific research alive, others as a would-be bomb builder who only failed due to practical or theoretical missteps. Yet the physics marched on. During the 1940s and 1950s, quantum mechanics expanded into quantum electrodynamics, QED, spearheaded by Julian Schwinger, Richard Feynman, Shinichiro Tominaga, and Freeman Dyson. Although Heisenberg contributed to early quantum field theory, the next generation carried the torch forward, making the theory fully renormalizable. Schrödinger's wave mechanics remained indispensable as a foundation for solving countless quantum problems, from nuclear shell models to condensed matter physics. Even as global politics changed, the theoretical bedrock that Heisenberg and Schrödinger had built continued to support new breakthroughs. Philosophical debates also persisted. Schrödinger's cat paradox, introduced in 1935, gained new traction post-war as more philosophers of science and physicists turned their attention to foundational issues. Some, like David Bohm in the early 1950s, proposed hidden variable theories that aim to restore determinism, though these typically involved non-local processes, as John Bell would show in 1964. Others, like Hugh Everett in 1957, advanced the many worlds interpretation, sidestepping collapse by suggesting the wave function never collapses but branches into multiple worlds. While neither Heisenberg nor Schrödinger fully embraced these alternatives, their earlier work laid the foundation for such reinterpretations. Heisenberg, re-ensconced in Germany, wrote several treatises on the philosophical implications of quantum theory, often referencing ancient Greek philosophy and emphasizing the limits of human knowledge. Schrödinger's interests grew ever broader. After What is Life, he delved into mind and matter, exploring the role of consciousness in the physical world. He became fascinated with Vedantic philosophy and tried to reconcile Eastern monism with quantum principles. This bridging of science and spirituality was not well received by all physicists, but it demonstrated Schrödinger's persistent drive to see unity in the world's phenomena. Meanwhile, the memory of the cat paradox lingered as a testament to the interpretive puzzles at the core of quantum mechanics. Although it was framed partly as a criticism of the Copenhagen interpretation, it lived on as a staple thought experiment beloved by philosophers and students. Over time, Schrödinger's cat became an icon of popular culture, symbolizing the strangeness of quantum superposition. This was an ironic twist. Schrödinger had intended it to highlight the problems in standard quantum theory, yet it became a simplified poster child for that very theory's bizarre predictions. For Heisenberg, the post-war years were a mixture of rehabilitating German physics and refining his ideas about the quantum world. In 1955, he published Physics and Philosophy, where he addressed the shift in worldview required by the quantum revolution. He argued that quantum theory did not destroy the possibility of objective knowledge, but rather placed constraints on how we frame that knowledge. In 1958, Heisenberg moved to direct the Max Planck Institute for Physics and Astrophysics in Munich, where he worked on unified field theories. Although none of these unified approaches panned out in the manner he hoped, it testified to his lifelong ambition to find overarching frameworks that might reconcile quantum theory with other fundamental forces. Meanwhile, Schrödinger eventually returned to Vienna in 1956, resuming a post at the University of Vienna. He died there in 1961. Heisenberg survived longer, passing away in 1976 in Munich. By then, both men had witnessed the transformation of quantum mechanics from a marginal, scandalous set of ideas in the mid-1920s to a foundational pillar of modern physics and technology, from transistors to lasers to nuclear reactors. Their two formulations, wave and matrix, remained in textbooks side by side, each one a testament to their author's genius and distinct philosophical leanings. World War II thus served as a tumultuous backdrop to the personal journeys of Heisenberg and Schrödinger, but it did not diminish their scientific legacy. If anything, the unleashing of nuclear power underscored the potency of quantum theory in revealing nature's secrets and the moral weight that came with such revelations. In Episode 5, we turn to a closer look at their philosophical outlooks and the culminating achievements of their careers. We will also explore Schrödinger's foray into biology in more detail and see how his famous book, What is Life?, influenced the nascent field of molecular biology, arguably reshaping the intellectual landscape far beyond physics. Episode 5: Philosophical Quests, Cats, and Life. Throughout the 1930s and 1940s, as quantum mechanics grew from a contentious new theory into an established pillar of physics, both Werner Heisenberg and Erwin Schrödinger continued to wrestle with questions that went beyond the scope of mere calculation. Each harbored a sense that physics was not only about producing empirical predictions, but also about clarifying humanity's understanding of reality. Yet their approaches were markedly different, shaped by temperament and circumstance. Heisenberg, the epitome of a structured mind, believed that the new physics implied a fundamental shift in the way we relate to nature. He saw no way back to classical realism and believed that attempts to speak of what really happens between observations could lead to confusion. For him, quantum mechanics taught that certain questions were simply meaningless unless cast in terms of observables. He wrote extensively on these views, drawing upon philosophical traditions from Plato to Kant. In his later years, through books like Physics and Philosophy, Heisenberg attempted to communicate to a broader audience how quantum principles limit the scope of human knowledge and yet open up new avenues for understanding the unity of nature. Schrödinger, on the other hand, was far less satisfied with the notion that quantum mechanics might forego a robust description of reality. He was, from his youth, a thinker prone to wide-ranging intellectual pursuits, poetry, Eastern religion, philosophy. Even as wave mechanics gained universal acceptance, Schrödinger remained a skeptic regarding the measurement postulate. He introduced the cat paradox precisely to dramatize how bizarre it is to treat the wave function as physically real for microscopic events, only to abandon that realism for macroscopic observers. These philosophical concerns stayed with him throughout his life, leading him to explore alternatives, though none gained mainstream acceptance as a replacement for the Copenhagen paradigm. It was this same philosophical disposition that drew Schrödinger's attention to biology. He had a long-standing interest in living organisms, influenced by the writings of philosophers, naturalists, and his own sense of wonder about consciousness. He gave a series of public lectures in 1943 at Trinity College, Dublin, which formed the basis of What is Life?, published in 1944. In this short but profound text, Schrödinger asked how living systems maintain high order, low entropy, in apparent contradiction to the second law of thermodynamics. His answer hinged on the concept of negative entropy, or free energy, being extracted from the environment. More famously, though, he speculated that genes might be represented by an aperiodic crystal, suggesting a molecular structure that encodes hereditary information in its arrangement of atoms. This speculation presaged the discovery of the DNA double helix by Watson and Crick in 1953. Schrödinger's influence on those researchers was profound. They openly credited What is Life? As an inspiration. Although Schrödinger's quantum expertise did not translate directly into elucidating the structure of DNA, his call for a molecular explanation of life and his vision that quantum laws might undergird biological stability resonated powerfully with the young scientists who would build molecular biology. In that sense, Schrödinger contributed indirectly to a paradigm shift in biology analogous to the quantum revolution in physics. Heisenberg, while never venturing as deeply into biology, remained attuned to broader scientific questions. After the war, he led the revival of German physics, presiding over institutions that fostered new research in high-energy physics, cosmology, and the search for a unified field theory. Throughout the 1950s and 1960s, he engaged in dialogues with philosophers, theologians, and the general public, attempting to clarify the meaning of quantum mechanics for a Western audience shaken by the war and the atomic bomb. He argued that the new physics reinforced the notion that nature cannot be reduced to mechanistic materialism and that the classical separation of subject and object was, in many ways, a convenient fiction undone by quantum experiments. Despite their philosophical differences, Heisenberg and Schrödinger shared the belief that physics had to be more than a specialized, purely technical endeavor. Each saw the quantum revolution as a signpost that human knowledge has limits and that nature resists certain forms of simplification. In letters and occasional meetings, though their direct interactions grew fewer as time went on, they maintained cordial respect. Their once heated disagreements over matrix versus wave mechanics had been overshadowed by the recognition that both representations were, in fact, complementary aspects of a deeper formalism. If Heisenberg's lasting theoretical fingerprint was the uncertainty principle, Schrödinger's was undoubtedly the wave equation. Both were taught year after year to students around the globe, ensuring their place in the pantheon of modern physics. The philosophical paradoxes they uncovered, the measurement problem, uncertainty, wave-particle duality, also remained front and center in advanced courses and debates. Many new interpretations, Bohmian mechanics, many worlds, relational quantum mechanics, would be proposed, but the core mathematics and the phenomena it described would stay the same. To the broader public, Schrödinger's cat took on a life of its own. By the 1950s and 1960s, references to the cat paradox began to appear in both scientific discussions and popular culture. It became a playful shorthand for quantum weirdness. Schrödinger, somewhat amused but also exasperated, realized that the cat had overshadowed his original intention to highlight the interpretive difficulties of wave function collapse. Nonetheless, Schrödinger's cat became a kind of philosophical Rorschach test, prompting every new generation of physicists and philosophers to wrestle anew with what quantum mechanics says about reality. During these years, Heisenberg also participated in discussions about nuclear policy, disarmament, and the role of scientists in public affairs. He joined the Göttingen Manifesto in 1957, opposing the arming of West Germany with nuclear weapons. Despite lingering controversies about his activities during the war, many saw Heisenberg as a moral voice in the post-war era, cautioning against the unchecked use of science for destructive ends. By the 1960s, as both men advanced in age, quantum mechanics was no longer the rebellious newcomer in physics. It had been integrated with special relativity to form relativistic quantum field theory, and it served as the bedrock for solid-state physics, nuclear physics, and early particle physics. The next wave of questions, about quarks, the strong interaction, the weak interaction, and eventually the electroweak theory, arose from quantum ideas but were tackled largely by younger physicists such as Murray Gell-Mann, Sheldon Glashow, Abdus Salam, and Steven Weinberg. Still, every step they took bore the imprint of Heisenberg's and Schrödinger's foundational work, especially in the underlying mathematics of operators and wave functions. Schrödinger passed away on January 4, 1961. In his final years, he had been active, writing about color theory, consciousness, and the mind-body problem, always pushing boundaries. He left behind a legacy that transcended physics. He was a Renaissance figure who saw science, culture, and philosophy as facets of the same quest. Heisenberg lived on until 1976, continuing his involvement in German scientific institutions and occasionally publishing on unified theories and the philosophical underpinnings of quantum physics. When he died on February 1, 1976, an era truly ended. The quantum pioneers, Planck, Bohr, Born, Pauli, Dirac, Schrödinger, and Heisenberg, were all gone, leaving behind the second half of the 20th century to further refine and apply the revolution they had set in motion. In Episode 6, we will explore the ultimate legacy of Heisenberg and Schrödinger, seeing how their breakthroughs not only transformed science but also influenced broader human thought. We will reflect on the ways in which wave mechanics and matrix mechanics have persisted in contemporary physics, how Schrödinger's philosophical forays shaped interdisciplinary research, and how Heisenberg's uncertainty principle remains a cornerstone of our understanding of the quantum world. Finally, we will examine how their ideas continue to resonate in the 21st century, from quantum computing to quantum biology, demonstrating that the work of these two giants still reverberates across multiple frontiers of knowledge. Episode 6: Legacies in the Quantum Age. The story of Werner Heisenberg and Erwin Schrödinger is, at its core, a tale of two extraordinary minds who helped redefine reality for the 20th century and beyond. By the time of Heisenberg's death in 1976, quantum mechanics had become the undisputed framework for understanding the microscopic realm. Experiments in atomic, molecular, and optical physics consistently verified predictions made by the quantum formalism. Solid-state physics led to the transistor revolution, integrated circuits, and the digital age, all resting on quantum principles. Nuclear reactors and nuclear medicine also owed their development to the quantum unraveling of atomic nuclei. In short, the transformations that Heisenberg and Schrödinger helped set in motion impacted every corner of modern society, from electronics to healthcare to the geopolitics of nuclear armament. The two primary formulations of quantum mechanics, Heisenberg's matrix mechanics and Schrödinger's wave mechanics, remained pillars in physics education. Textbooks worldwide present both pictures to students, typically in the first or second course in quantum mechanics, emphasizing that they are mathematically equivalent. The operator approach remains especially convenient in advanced quantum field theory, where creation and annihilation operators lie at the heart of describing particles. Schrödinger's wave equation, on the other hand, is indispensable for non-relativistic quantum problems: atoms, molecules, quantum wells, lasers, and much more. The synergy of both approaches is perhaps the clearest vindication of the fact that these two men found different ways to express a single underlying truth. Heisenberg's uncertainty principle, taught as a fundamental property of quantum systems, lives on in cutting-edge technologies. In quantum optics and quantum information theory, uncertainty relations connect to the phenomenon of quantum entanglement. Quantum cryptography, for instance, exploits the no-cloning principle and uncertainty to guarantee secure communication. The principle also underpins ongoing debates about the nature of quantum measurements and the boundary between classical and quantum domains. Schrödinger's cat, too, has seen renewed life in the new millennium. Quantum decoherence theory, developed by researchers such as H. Dieter Zeh, Wojciech Zurek, and others, offers a partial explanation for why superpositions become less visible at macroscopic scales. Experimentalists have managed to place larger and larger systems, including molecules of decent size, into quantum superpositions, thereby testing the fuzzy boundary between the quantum and classical worlds. Although we do not yet see living cats in quantum superpositions, the conceptual framework Schrödinger illuminated continues to guide experiments at the cutting edge of quantum science. Beyond physics, Schrödinger's intellectual curiosity and philosophical writings have had a lasting influence in fields such as systems biology, cognitive science, and the philosophy of mind. What is life retains a certain timelessness, reminding scientists that foundational questions in biology are intertwined with questions about order, information, and quantum effects. Even as molecular biology advanced beyond Schrödinger's initial speculations, the impetus he provided remains deeply acknowledged by historians of science. Heisenberg's own philosophical outlook, bridging quantum mechanics with a form of realism tempered by the limits of knowledge, resonates in contemporary debates about the role of observers, the interpretation of probability, and the meaning of scientific theories. Some interpret Heisenberg's stance as a precursor to relational or epistemic interpretations of quantum mechanics, in which the quantum state is seen as a state of knowledge rather than a literal physical wave. Although he did not formulate these ideas in the same way as modern proponents, Heisenberg's emphasis on observables and measurement continues to inspire new lines of thought. Culturally, the quantum revolution has seeped into literature, art, and popular discourse. Terms like uncertainty principle and Schrödinger's cat have become metaphors in everyday language, sometimes used loosely or incorrectly, but always signaling a sense of paradox, duality, or unknowability. Films, novels, and plays have incorporated quantum themes to explore questions of fate, identity, and free will. Even if the technical details remain elusive to the public, the symbolic power of these concepts is undeniable, a testament to Heisenberg's and Schrödinger's achievements transcending scientific circles. As the 21st century unfolds, quantum mechanics continues to expand into new domains. Quantum computing, once a speculative idea from the 1980s, is now pursued by major corporations and research institutes seeking ways to harness superposition and entanglement to solve problems classical computers find intractable. At the heart of quantum computing is the wave function and the operator formalism, both direct descendants of the pioneering works by Schrödinger and Heisenberg. Questions about the speed-up possible via quantum algorithms and how errors might be corrected in a quantum system reflect the same fundamental principles first discovered nearly a century ago. Quantum biology, too, has emerged as a nascent field, investigating whether quantum coherence plays a role in photosynthesis, enzyme reactions, or even bird navigation. Though the degree of quantum effects in warm, wet biological systems is debated, the field owes a nod to Schrödinger's early recognition that life might harness quantum processes. Regardless of the outcome, the impetus to look for quantum phenomena in living organisms flows from the possibility that nature at every scale could reflect these fundamental laws. Heisenberg and Schrödinger also remain exemplary figures of how science proceeds through divergent yet complementary insights. Their rivalry in the mid-1920s was genuine. They came up with apparently contradictory approaches to quantum phenomena, but it led to a deeper synthesis once the equivalence of matrix and wave mechanics was established. This synergy is a reminder that science thrives on multiple perspectives, intellectual tensions, and the interplay between abstract mathematics and intuitive analogies. Their personal stories also serve as cautionary tales about the intersection of science and politics. Heisenberg, caught in Nazi Germany, found himself navigating a moral and ethical minefield. Schrödinger, forced into exile, made significant contributions away from his home country. Their experiences underscore that scientific progress does not occur in a historical vacuum. It is shaped by economic, political, and cultural forces that can either nurture or stifle inquiry. Today, historians of science rank Heisenberg and Schrödinger among the pantheon of 20th century intellectual giants, akin to Einstein and Bohr. Their breakthroughs, especially Heisenberg's uncertainty principle and Schrödinger's wave equation, remain indispensable. Every student of physics must learn them. Every advanced technology at the quantum frontier builds upon them. Philosophers and theologians continue to reflect on the implications of quantum mechanics for questions about determinism, free will, consciousness, and the ultimate nature of reality. Thus, the pioneering work of Werner Heisenberg and Erwin Schrödinger was not merely a historical episode, but the opening act of a transformative epoch in human thought. They forged two paths, operator algebra and wave equations, to glimpse the underlying machinery of the universe. They revealed that, at the smallest scales, nature defies classical intuition, demanding a radical rethinking of knowledge, measurement, and existence. They inspired future generations not only to refine quantum mechanics, but also to explore entirely new realms, from the nucleus to the genome, from supercomputing to cosmic structures. In final contemplation, one might imagine the youthful Heisenberg on the island of Helgoland, plagued by hay fever, but driven by the question of how to remove unobservable electrons from the theory, working tirelessly at night under the stars. Meanwhile, an older Schrödinger, in his Dublin study, pondering how quantum laws might illuminate the enigma of living matter, drafting his lectures that would spark the imaginations of biologists to come. These two scenes, separated by time and geography, encapsulate the range and depth of their quests, at once technical and philosophical, mathematical and human. Their legacy endures wherever atoms are probed, wave functions are solved, or the fundamental nature of reality is pondered. It is the legacy of two minds that changed the world by uncovering and articulating nature's most subtle and beautiful truths.